Said a protocol is a blueprint that lists properties, methods, or initializers that a conforming type needs or is required to implement. Right? So here we're saying a protocol is a blueprint, a template, right? Just a list of things that you have to do. Is a blueprint that lists properties, methods, or initializers that a conforming type is required to implement, right? So there's two things. There's the protocol. One second. There's the protocol, and there's the class or the struct that's conforming to that protocol. Let me get my Xcode running again. Sorry about that. Okay, so there's two things here. The protocol is that thing that discusses or implements the methods, the properties, not implements, but lists the properties, methods, and initializers. And the conforming type could be an enum, a struct, or a class, right? So that conforming type here could be an enum, as we saw earlier in Unit 1, a struct, or a class, right? The basic definition of a protocol, you start out with the keyword protocol, the name of the protocol. Here we'll just say some protocol for now. Again, it's the same convention as we have had with classes, structs. You start out with an uppercase letter, followed by comma cases if you have all the words in there. So some protocol is uppercase S. Here we have properties that this protocol is listing. So here we have our properties. This property is a variable. It's some string, which is a string. And we haven't seen that syntax here, right? So that syntax says it's a getter and a setter. So some string, whoever is conforming to some protocol has to implement some string, and some string needs to be able to be settable. The get here is I need to be able to get a value from it, right? I need to be able to get what some string is. But it's required that this some string not be a constant. The some string cannot be a constant. I need to be able to set it, right? This is the set word there, that set keyword. I need to be able to set some string and also get it. Everybody with me? So get here and set is required by that conforming class or struct. We'll see what that looks like, but now we're just listing. This is the blueprint. There's no definition here. I'm not saying some string equal to 0, right? Like that. That would be a compiler error. The protocol cannot have a stored property, right? Look, already it's saying initial value is not allowed here. Everybody with me? The protocol only lists what the thing is required to implement. The thing here is a conforming type, okay? So here, let's go back. So here I have some string. I'll have a next property called some int of type int. And here we see only get, right? The conforming type could also set, but I'm not requiring them to set. It could be a constant. It could be a computed property, right? The conforming type just needs to implement some int, like have a some int in their object, okay? We also said you could have methods in a protocol. So here I will have a function called some method. We could also have a mutating method in here, some mutating method. Right? If we were to go ahead and use this on an object, for example, I define a struct, call it some struct here. The way you conform to a protocol, as we saw in enums with case iterable, how do we conform to a protocol? I have a struct called some struct. How do I conform to a protocol? Yes. So as Chelsea is saying, everybody heard that? So Chelsea is saying you put a colon after some struct name, right? Adam, is that familiar? And the name of the protocol we want to conform to. In that case, it's some protocol, right? So struct is our type. Some struct is the name. And to conform to some protocol, we say colon and the name of that protocol. Right? So that's the basic syntax of conforming to a protocol. And already we see in the compiler is throwing errors because we said, hey, we agree to conform to this protocol, but we haven't implemented any of the requirements. All those here are requirements. If I'm saying I am conforming to some protocol, I have to implement in some struct, some string, some int, some method, and some mutating method. Everybody with me? Right? We'll talk about optionals at the end, or maybe we'll hold that off for now. But you could have your protocols having optional methods where you don't have to implement it. Yes, sir? You have to use all the properties of the protocol? Yes, in that case, they're all required. Very good question. So Christian was saying, do you have to use all the properties of the protocol? Yes, you do. It doesn't show explicitly required, but they're all explicitly required. By default, they're all required. At the end of the lesson, we might get to talking about optionals, optional protocol types and stuff. But for now, all what we have here before us, we have to implement it. That's what the compiler is saying here. If we click on the error, it says type some struct does not conform to protocol. Do you want to add protocol stubs? Right? For now, we're not going to go ahead and fix it, but you could very simply click the fix it button, and it will give you all the stubs required. Okay? But to get us used to implementing a protocol ourselves and knowing what the syntax looks like, we won't click on the fix it button. Everybody with me? Okay. So let's go ahead and conform. Conform basically means I'm a type. I'm saying I'm agreeing to take your license or whatever, your requirements. I'm agreeing to implement all those requirements. I made an agreement with you. I'm in contract with you, right? That's what conforming means. I'm conforming to some protocol. I'm agreeing to implement all the requirements. Everybody with me? The one that's conforming, some struct is the conforming object, right? Some struct here, conforming object conforms to some protocol, right? You could say conform enter agreement whereby this type will implement all required or all listed required properties, methods, and initializers. Right? So that's what conforming is there. I'm entering an agreement with this protocol. I'm saying that anything that you require, I will implement. Any questions? Any questions with the syntax on the protocol? With the curly bracket, the get, and the set? Yes, sir.
It's just weird with the get set normally between like statements like a comma or it's just straight get.
Exactly. So it's unique to protocols the way we define it. So the way we define it, we say variable or whatever it is. It will be a variable because you need to be able to set it or mutate it. The name of that variable, the type of the variable, and in the curly bracket here, you need to say, is it a get only? Right? Is it a get only property? Or do you need to require that some struct have a way to set that property? If some struct comes here and they say I'm a constant, right? It will throw an error. You need here, our sum struct needs a way for the user to set some string at any time, right? That's what the set is saying. The set is saying, I need to be able to change the variable. The get by itself, it's valid if I have a computed property. Just return something. But this one will give you a compiler error if you have a computed property and not a way to set that property, right? Everybody got that, right? So one's question was, again, he wants to go over what the syntax looks like here and what that means. The first on line 7 says, you cannot have a constant. You cannot define some string as a constant. You cannot define some string as a computed property. We know what a computed property is, right? A computed property returns some value. That's all it does. It returns some value. So here, I need to be able to get a value and be able to set a value, right? With the get set. Explicitly on the protocol, I'm saying on some string, I want the client or the user to be able to retrieve a value and also change that value. A computed property, you cannot change the value, right? Everybody? Yes. In theory, the some string could be a let. On the struct itself, the implementation of the struct, yes. Okay, so let's go ahead and conform, meaning let's go ahead and implement the requirements of the sum protocol. Okay? So the first thing we'll do, if we go to our sum struct, we'll start typing some string, and it's gonna come up because it knows some string, okay? So at that point, I could press enter. So some string, for now, let us do some string. I'll show you guys what I mean by that. So if I say return hello, like that, right? What type of property is this? It's a get, right? But it's a computed property, right? It's a get, meaning it only gets your value. Very good. My next variable, I have some int. And some int, I could set it to 0. Compiler is still not quite happy because we're missing what? We're missing 2 methods to implement. Everybody? So my sum method, I type in some method, just print out for here, we'll just print out some method here. And lastly, we have our last method called some mutated method. I'll also just print out some mutated method. Right? But the compiler is still not happy, right? It still sees that we're not fully implementing our protocol, right? We're not conforming to the protocol. Anybody could tell me why? Minus the mutating here. Anybody could tell me why? Yes. So this is initialized, it has a value. This guy returns some value, hello. Yes, sir. The sum string never got anything. Let's see. So a set, right? Who said that? Right? So according to Adan here, we do not provide the sum struct a setter. There's no way to set sum string, right? Because now sum string is only a getter. This is very important because that's where you're like, why I'm having a get set here, right? What's the point of it? The point of it is right here. I'm only having a getter. I'm not saying sum struct could set sum string. Do we see that? There's no way for me to set this. If I go to my compile, if I go to my playgrounds and I do, I create some struct instance here, and I say some struct. I say some struct, and I give it 8, whatever, here, right? If I go down to some struct, let's here. I go down to some struct and I say some string. Change this to like message, for example. Make this a var. Right? Here it says cannot assign to property some string, right? Cannot assign to property some string. Some string is a get only property. Do we see that? Right? On our playgrounds here, we cannot set some string. Our protocol says, or our protocol is telling us, we need to be able to set some string. Right now, we cannot set some string. I cannot say some struct that some string equal to something. I cannot assign it a value, right? Because of my computed property here, right? So this is a compiler error. The way I could change this, right? Let's go ahead and change this. I could simply take out my computed property here, set some string to some empty string, like that. Right? At this point, I'm able to set some string. My compiler error goes away. Everybody sees that? Let's really drive the point home. So if I go on my sum int here, and I say return 10, for example, right? Will I get a compiler error? Right? I get a compiler error because this guy is set already, so I need to remove this. Because I have a value. I'm returning a value from sum int. Sum int returns a value. I cannot change it. Right? At this point, it's not mutatable. It's immutable. Right? It's immutable. I cannot change it because this is a computed property. Right? Compiler is happy because my sum int on my protocol is a getter. It doesn't need to be setter. Right? It doesn't need to be a setter. So the compiler is also okay here, because sum int is a computed property, right? This is allowed, but it's not allowed on some string because some string has a setter. Again, this is like new syntax to us, but for now, let's just know that if I have a get only in my bracket, that means I could have a computed property being returned, okay? If I have an explicit set, that means I cannot use a computed property. I need my type to be able to change that property, right? Here, some string could be changed. I go down here, I change some string. Everybody with me? Any questions with that? Any questions so far? We could go over it again. Yes, sir.
So you have a get, you could use a computed property.
Yes. Because there's no set there on my protocol. Okay? My protocol says it's up to me what I want to do. I could have a setter, but it's not required. Okay? That's what the get by itself says.
Or you can set it,
You could have a stored property,
store property,
or you could have a computed property.
just don't change the store property.
Just done what?
Don't change the.
You could
You
have,
have a get and you can't change.
if you have, like, that's a getter, right? I cannot change
Right, so
what,
if you have a set, then
you could change it, yeah. But the compiler is still going to be okay with that. It could go, for the get, it could be both ways. For the get and set explicitly, you need to have a setter. You need to be able to change that value. Yes.
Is there a circumstance without a get? Like, could you do just a set, for example? Or does it require a get?
It needs to have a get. Yeah, it needs to have a get. So most times you'll see, again, it's up to you what your intentions are. But most times get is okay by itself. But it depends on your circumstance. You could have a get or set. But those are the two circumstances. You need to have a getter to be able to get a value. And it's up to you if you want to be able to have the user change that value or not. We'll have more examples, but that's like the template example we have. We'll have more examples later. Because every protocol we do from now on will have a get or a set or both. Cool? We'll have a next example. Okay? Actually, let's make an example now. So let's create a protocol here. Let's see. Let's call it programming language. Actually, let's change this. Let's change it to race here. A race has a type. A race has a type, which is a string for now. And we'll say it's a getter. And the race has a distance. We'll say it's an integer. So we're saying you could change, right here. So we'll say you cannot change the distance for now. It's a getter. And for the type, same thing, that's fine. And for the name, we'll make it both a setter and a getter. Great. So we have a protocol called race. The name will not be an int, it will be a string. Thank you. And I'll create a struct, call it marathon.
So the order in which we write it says
No, it doesn't. And then here we have a struct, call it marathon, and it conforms to race. And then just have an info function here. So function info. Cool? So here we have a protocol, it's race. We have three properties. We have a type, distance, and name. And we have a function called info. And here we have a struct called marathon. It conforms to the race protocol. So let's go ahead and implement that protocol. So we know we need a type. For the type, I will say, I'll just return it's a marathon. So here I'm using a computed property, right, Mel? Right, so that's a computed property here. Its type, it returns a string, right? This is a string, so far so good. Next up, we have distance. We'll return, let's change this to a double. What's that? Oh, it was great, actually. Beautiful day. So here we'll return a double. So here I'm returning 26.2 for the name. So the name, we could set the name, right? So let's go ahead and do that. So if I say I'm using a computed property for name, and I say return New York City Marathon, like that. This is also a computed property. Well, this needs to be a double. And lastly, we have our function info. And here we'll simply print the race name, the name is a type and is x distance long. Right? At this point, we've implemented all the requirements, correct? Correct? How many properties do we have? How many properties do we have? 3. How many methods do we have? 1. But the compiler is still saying we are not conforming to race. Anybody could tell me why? We didn't set it again, right? We're not providing a setter for name. If we see name, name explicitly says, I need to be able to set. I need to be able to set name, meaning I need to be able to change the name of the race. Right? Here, we're not doing that. We're going ahead and we're saying, oh, just return NYC Marathon. Right? I don't care what it is, just return NYC Marathon. That does not compile because my protocol, I'm not adhering to my protocol. My protocol said, not only do I need a getter, but I need a way to set this variable. Right? So the way we could change it is simply saying name here equal to New York City Marathon, like that. Right? At this point, it's a variable. Can I change a variable? Can I mutate a variable? I can, right? I start out with a default being NYC Marathon, but I could change that name. I could change that name. But what we had before was a computed property. We could only use computed properties if the protocol says it's only a getter. Okay, Cassandra? Right? If my protocol says I need a setter, I cannot only provide a getter here via a computed property. Okay? So that's the difference there between set get and get by itself. Mel? Mel? Helps you? Okay, cool. So this is, let's go ahead and test out our code, make sure everything works. So here I'll just create a variable called NYC Marathon here. It's a marathon. And here we see in our initializer, we could change the name if we want. So here I'll change the name to TCS New York City Marathon. And I'll go ahead and print out the info.info and run my playgrounds. And now we see the TCS New York City Marathon is a marathon, and it is, and right. So we saw that we overrode the name NYC Marathon to TCS New York City Marathon. Questions? Questions? Right.
So setting it actually.
Yeah, I could change it. I could mutate that value. You have to provide a way to mutate that value. Any other questions? Yes. For name. For name here?
Yeah.
Oh, why we need what's
Why setting the string?
Oh, it's okay here as opposed to, so this is, you agree that this is a computed property, right? This is a get only. I could only get a value from distance. I cannot set it, right? So distance here is a get only property. In that case, you need to return some sort of, whatever the value is, it's a double. You need to return what that type is. So here, distance is a get only property. Cannot mutate. Right, Christian? Right. If we do the same thing with name, if we say name is only a get only property, right, we're bridging the contract with the protocol. The protocol says name needs to be what? It needs to be needs to have a setter, and needs to have a getter. If we implement name as a computed property, we're saying we don't care about what you say as far as like setting the thing. I'm only going to provide a getter. And that becomes a compiler error because there's no setter. The compiler sees there's no setter, it throws an error saying you're not conforming to the type. You're still not conforming to the type because the type expects that variable to be changed. It needs to be changeable, or it needs to be mutable. And then making it a computed property doesn't make it mutated. Do you agree that distance, is distance mutated? Can I change distance here? Right? It's a get only. Right? Can I change type? No. Can I change name now? Because it has a setter. Right? Name here is both a getter and a setter. So I could both get the value. I could say nycmarathon.name, and I get what name is. And I could also say nycmarathon.name equal to something else. Right? So here it's both a setter and getter. We'll put some more notes here. So setter, example for setter, I could say NYC marathon, like that, dot name equal to, as we said down there, TCS NYC marathon. Right? That's a setter. That's a setter. Everybody, when I say setter, that's what I mean. I'm able to set the value. I'm able to change that value. Okay? Right? So the property is on the left side of the equal sign. I'm setting it. Okay? It's on the left side of the equal sign here. That means you're changing that value. Questions?
So without having a set, it only reveals marathon.
I could change it after. I could change it now because it also has a setter. Yeah, without, for example, here, this is only a getter. If I'm trying to change it, I'll get a compiler error. The compiler will say get only property, you cannot change. And for the setter part of this, we have, for the getter, we have example. Here, I could simply say, if we want to print something, I could say NYC marathon, like that, dot name. And then we'll get back, if we did change it up there, we'll get back TCS NYC marathon, like that. So this here is a getter. Get me the value, and print out what the value is. Right? Get me what the value is and print it out. So that's a getter here. Questions? Questions? But 1 second before I go down. If we try to do this example, if I try to use a setter here, attempt to use a setter to mutate distance, right? If I try to do this, if I try to say NYC marathon dot distance equal to 13.1, for example, will this compile? Line 54, will line 54 compile? Why? Because it's a get only, right? Everybody got that? Right? So Andrea is saying it's a get only because this is a computed property. It's a get only, as we also annotated here. So I cannot change what distance is. Right? I cannot change what distance is here. The compiler will not agree with that change. It will say it's a get only property. You cannot mutate it. Questions before we move on? No need to rush here. Did we finish? Let's see. So if your name is still a computed property, it's not going to compile. What's your name? No, but do you have equal to NYC marathon? Do you have distance? You have type? Do you have info? Back up where? This guy? Okay, so let's review. For the set and get, just do set and get here. The order shouldn't matter. You have the three properties and the function, correct? You have, yes, sir.
For right here, can you scroll up? Why the setter and getter?
Because, no. We assigned that string to name. And here we're just printing what the value is. Whatever we just assigned should be the same value, correct? Right? Here we assigned, if we printed it out before, it would just be NYC Marathon. If we printed it out before we set it here, it would just be NYC Marathon, correct? But here we change what NYC Marathon is to TCS NYC Marathon. So if we printed it, meaning get me the value, the value is what? Yeah, but what's the value of name? On line 61, what's the value of name? Yes, because we just changed it on 58. Does that make sense? Like we updated what name was, and now we're just saying, go ahead and print me what name is. Cool? Are we still getting the conforming error? Oh, okay. Most times you probably want to have the compiler help you with that one, like the autocomplete. Yeah. No, not to fix it. Like when you're typing out the required, yeah. Any other questions before we move? Anybody want me to go back over get set? Okay, I think we should just you guys create a protocol. Create a protocol and create a struct that conforms to that protocol, right? Create an instance of the struct. Create an instance of the struct and test. All right? So again, if you want to create like a person, maybe create like a protocol called walkable or whatever it is. Like create your own protocol, create a struct that conforms to that protocol. Give it at least two properties, right, everybody? Give it at least two properties and go ahead and use a struct that conforms to that protocol. Give it at least one function, and test it out. Cool? Say that again. Say that again, Christian. Yeah, give it at least one method. And for your properties, make at least one of them a set and get. Right? Like very similar to what we did here. It's very similar to what we did here. Right? So how about at least one of them being a set and get and one being a get only? Yeah. Yes. You could have an array. Yeah, very good. Yeah, I could have a protocol with an array of stuff. Yes.
So if extract inherits or
Not inherits, conforms.
conforms to the properties but it also can have its own properties.
Yes.
Is that
Yes, we'll see that in the next example. So Luba's question was, can my struct, in that case, can my struct marathon have its own properties? Yes, definitely. Right? So on my struct here, I could have location, which is a string. Luba? And here, just say New York City. Cool?
that's the difference, like
It's almost like inheritance, right? Like I inherit from my parent, but I could have my own properties.
but in classes when they inherit, they don't have to inherit.
Yes, exactly, exactly. Very good. Good observation there. If they're all required, you have to implement everything with the protocol. Yes.
Is it necessary to type annotate?
No, no. For the protocol, yes, but not for the struct. Yeah, yeah. Yeah, you're gonna go to change that.
get is both ways, a getter and a setter. But if you implement it with a limited property, that means you cannot set it at the time. Awesome.
Mr. Kelby, you want to show us your protocol? It's very.
Okey-doke.
Cool, thank you, sir. Kelby created a type Kelby. He created an instance Kelby. It's all about Kelby. Uh, very good. So at this point, we all created protocols. I saw interesting protocols as I was walking around. Yeah, so why protocols, right? That should be the next question. With classes, does a class have multiple inheritance, single inheritance? Single, right? So assuming we have multiple protocols or classes we want to inherit from, we cannot inherit from multiple classes. So far, so good, right? I can have like Kelby here, for example. He has a protocol, he's conforming to human, right? I can't also inherit from a next class. But with protocols, I could inherit from multiple protocols. I could inherit from human. I could also inherit from equatable or comparable or something else. With classes, you have single inheritance. So far, so good? So that's the difference between, that's what protocols gives us. Protocols gives us that ability to have multiple protocols I want to conform to. So if I have the struct Kelby and I have a different protocol, what other protocols we have here? Some protocol, right? So Kelby could also conform to some protocol. Here, right? So here I could have Kelby conforming to multiple protocols. I can't do that in a class. Everybody with me? Right? In classes, we do not have multiple inheritance. If you want to have all the attributes from a next class, it's not possible. So with protocols, you could have multiple protocols that a type conforms to. That's one of the biggest advantages to using protocols. Okay? So for now, I'll remove the sum protocol on human here. What are the protocols we have? Okay, so that's cool. Let's move on to our next example. Okay, so here we'll create a protocol called fully named. Was everybody able to create the protocol successfully and test it? Okay, so here I'll create a protocol called fully named, and it has a full name property, full name, it's a string, has a getter. I'll create a person. Do we have a person yet? Maybe not. Person conforms to fully named. And as Luba was saying earlier, right, person could have its own properties. So the person has an age, and the person has an occupation. Right? So here, person could also have its own properties, right? Person has age, person has occupation, and person conforms to fully named. So that means person needs to implement full name. Here, full name. And I could simply return right? Again, this here is a get only property. We can create a person, so far Bob or John equal to person, change Bob. Yes. Oh, sorry. Right. Why do I like to do that? Don't know. All right, thank you, sir. So here we have John, and it would be nice if John had an info here. Actually, let me see. Let me say that again. Oh, how can age be Bob Jones? That makes no sense. Age, let's put int here, sorry. And then age for Bob, let's do 4056, like that. All right, cool. I want to show us the next protocol that we'll see later in the lesson, but for now, I'll just introduce it to give us more practice with it. So first, if I go ahead and print John, like that, let's see what that looks like. So print John, just print John. Print John, what is John? John is here. So print John prints age 56, the whole object. It just prints the object for us, right? So we have an object, it's a struct, it prints what the object is and all the properties that object has. Everybody with me? Okay, we could take it one step further. We could conform to a protocol called custom string convertible. Custom string convertible gives us access to the property called description. Every object has a dot description on it. We've seen dot description on a character, right? We said character dot description. It gives us a string representation of it, right? Or number dot description, whatever it is. Every object has a dot description on it. We could go ahead and override what description is and pass in our own description for that object. In that case, person here, I could give it a description, and instead of saying person age 56, I could make a more descriptive, human readable description of what the person is. So let's go ahead and do that by using a protocol, right? So here we have, we'll see multiple conformance to protocols right here. So we have fully named, comma, I'm sorry, what's the question? So here we're going to do custom string convertible. We'll conform to custom string convertible. Already we're getting the compiler error because we need to implement description. If you're conforming to custom string convertible, you're required to implement description, right? So here we need to implement description. Description, computed property here, and we'll say return. All what it needs is a string. It doesn't care what the contents of the string is, but what description is looking for is a string. Everybody with me? That description here is coming from custom string convertible. Okay? The description here is coming from conforming to custom string convertible. Okay? In the string, we could describe what the object is. So here we could say full name is age old and is a occupation. Right? So earlier we had, when we printed out John said person, age 56, occupation web developer. Everybody sees my console? Right? Now if I was to run my playgrounds again and print John, I'll get a different description. I'll get the description that I passed in. Now it says John Appleseed is 56 years old, 56 years old, and is a web developer. Do we all see the console now? Right? So we've gone ahead, we've conformed to custom string convertible, we overrode the description property on an object. Remember, every object has description, right? We overrode what description returns. And then what description returns is a string, our own custom string. Okay? So this comes in very handy if you want to have your own object being printed in whichever manner that you want, right? And the way we do it, we conform to custom string convertible. Okay? Great. And let me run my project again. So that's good. John Appleseed is 56 years old and is a web developer. A protocol. It's built into Swift. right? So that's the second built-in protocol we saw. The first one we saw was case iterable. The second one we're seeing now is custom string convertible. It gives you access to the description property, description here on line 110, and now we're able to override. There's no override like explicit keyword there, but it gives us access to overriding the description, right? Everybody? Debug is for debugging purposes, but for production, meaning like if you want to ship your app to the store, you would probably want to use what you want to use, the custom string convertible option, not the debug option. All right.
Just for that, once you put it in custom string convertible, that's when the description then becomes a
Yes, because if you do not do that, very good observation. If you do not do that and you just say var description, that's your own description. Right, everybody with me? So if I do not explicitly say description here, like that, right? The description that I have now is my own description. No longer will, like if I run the program again, no longer will I get description. I'll go back to what person age 56 was earlier. Everybody notice that difference, right? So just saying description without conforming to custom string convertible is not enough. Everybody, the compiler sees description as our own description. Does that make sense? Any questions about that? Mel? Okay, so description, like you see on our print statement, it says print John, correct? If we print John, what comes out is the actual object, what that object has. It says person, open parens, age 56, occupation, web developer, right? But that's not descriptive enough, like for somebody to read, like just reading, like from a sentence. So we went ahead and we said we want to have our own custom description, Mel, right? In order to do that, you could have your own description like this and say dot description, like that, right? Right? But that doesn't read correctly, where Swift has a built-in description already. Right? So Swift has a built-in description already, but we need to get access to it. How we get access to it? We conform to custom string convertible. When we conform to custom string convertible, by typing it in, now we're conforming to custom string convertible. That description now is part of Swift. It's built into Swift, so we're not saying John.description. It's already built in. It's inferred now. And if we run the program again, our string will be printed out. Does that help? Okay. That's the most common one used, right? Any questions before we move on? Yes. Protocols that's built in to Swift. I was looking for one explicit link. There's, at the bottom of our lesson, those are the more common ones that we will come across. So if you go to the very bottom, not the very bottom, at number 8, if you go to number 8 in our lesson for today, you'll see the most common protocols that's used in the language, right? Do we see that, access to that? Let me zoom in. Case iterable, we've seen from enum. Equatable, we'll see today. Comparable, we'll see today as well. Hashable, we'll start seeing more of that as we go deeper into data structures. Collection and sequence, we'll also see as we go deeper into data structures. And custom string convertible, we saw today. Cool, there's many more, right? But as far as like a link with like, I'll come across, I'll see if I can get one. If somebody gets one, share it to the, share it on Slack. But for now, those are the basic common ones that we'll be talking about. What's that? You cold? I'm still hot. Yeah, but majority rules there. Mel, question? Okay. Any questions before we move on here? Okay, so let's go. Great. So here we had our person, and now we could simply say print John and John prints out what's on line 111. Because we went ahead, we conformed to custom string convertible, we got access to the built-in description on an object, and we were able to return a custom string that we created. So far, so good? Okay, cool. Did an example of this already. I'm not going to do that again. Yes. Here. Mm. You mean what we got before we did the custom string convertible? Okay. Oh, why did full name come up? Oh, because full name has a value already. The member-wise initializer only gives us options that doesn't have a value. Cool? Good, good, good. So Amina's question was, why didn't full name come up as an option for our initializer? First of all, that's a compiler error, right? Because full name is only a getter, right? Second, full name has a value already. Cool? Very good question. Okay. Let's move on here. Okay, so sticking with person here, person has an age, person has an occupation. Great. Let's create an next person instance. So far, Greg, 1G today. He's 19, look at that. And he's a Ruby developer. Cool. So we have two instances. We have John and we have Greg. They're both people. They're both person objects. So why not, let's try to compare them. So if John equal to Greg, then we simply print out it's the same person, else different people. Right? Okay, we have a compiler error here. Binary operator cannot be applied to two-person operands, right? So here we have operand 1, operand 2. We have our binary operator here. Basically, we're trying to see if is John equal to Greg, right? On our custom object, which is person. But this is not valid, right? Person does not give us a way to find if one is equal to the other. We could say if John.age equal to Greg.age, we could do that, right? But here we want to compare two custom objects, right? If you want to compare two custom objects, you have to conform to a next protocol. Anybody want to give me a hint here? What are the protocols? Comparable is one. Equatable, right? Let's try equatable. We'll conform to equatable. Equatable gives us access to compare two objects together, right? Via equal or not equal. Yes, sir. For here, we'll define what the equatable is. So simply conforming to equatable, let's go up to our definition, our person object here. So we'll conform to equatable. Is there a limit? That's a good question. As far as I know, there's not a limit, but at some point your object, after you get to 3, 4 protocols, you probably got enough of what you need. Then you could probably have an extension on that type or redefine what your type should be altogether. Yes?
And you don't put the custom string on the equatable, you don't put it on the original protocol.
So our person, we have our person object. We conform to fully named earlier, right, to get access to full name here.
Oh, and that's because we made that protocol, but the rest of them are already in there.
Those are built in.
Oh,
The compiler even lets you see that, right? Like the purple one is the built-in protocols, and for me, the light greenish color is the very good. So now we have equatable. Before Swift 4.2, I think, right? When you did equatable, you would have to specify like a static function and define what the equatable is here. But for now, equatable by itself was enough. And now we could test it. We could run our playgrounds. And here, they're different people, right? So John and Greg are different people. What Swift does, Swift takes all our properties here, it compares all our properties against each other, and it figures out, are they equal or not? Okay? Everybody? Right? I have an age property. I have an occupation property. Is age equal to age? Is occupation equal to occupation? Well, first of all, the minute age is not equal to age, it's no longer equal. Everybody with me? So the compiler goes through the properties that you have, and it figures out, is those two objects equal? Okay? So that's for equatable here. Actually, let's test out. Do we have a fellow? Let me make you guys do your own. Yes, sir.
Does Greg fully equal
They're not equal. They're different people.
what is Greg's name?
Greg, what is Greg's name?
What is Greg's name?
They're both the same name, but the rest of the properties are different, right? Yeah. They would be the same. Like if I printed out Greg dot full name, it would be the same John Appleseed, right? But that's not the only property we're looking at. Yeah, exactly. All right, so let us do one example ourselves here. So create a movie struct. Create a movie struct and conform to equatable. Create a movie struct. Create 2 instances of movie. Test your solution. So create a movie struct, create 2 instances. So create 2 instances of movie and conform to equatable. No, you're not creating a protocol for those. We're still talking about protocols, but you're using the built-in protocol, equatable. And then create a fellow struct. Create 2 instances of fellow. And create 2 instances of fellow. For your movie, have at least 2 properties there. So create a movie, create 2 instances of movie, create a movie. right? So like name maybe. Name and genre is probably enough. Create a fellow struct, create 2 instances of fellow. Create properties. Fellow has a name. Fellow has, there's a name and a part, that's enough here. Then compare. All right, for the second one, create a fellow struct, create 2 instances of fellow, create the following properties like a name and cohort. Cohort should be double here. And name is a string. Then compare the fellow instances to verify who is the most recent cohort. Who is, yeah, in the most recent cohort, most recent being 6.0. First fellow instance should be 5.0, and the second should be 6.0. Is that clear enough for number 2? Right? And number 1 is just like create a movie struct, declare at least 2 properties in the movie struct, a name and a genre, create 2 instances of movie, and conform to equatable, test your solution. Is one movie equal to the next? And for the fellow example, it is this fellow 1 greater than fellow 2. Yes? We're not doing specific properties within the actual object.
Yeah, I'm just asking, can you use this here with properties? Like, let's say they're the same genre.
You don't need that actually. If you're doing properties, most likely it's a built-in property type. You wouldn't need equatable. Does that make sense? Like if we have to go back to our example here, if I want to say if John.age, if we have an age here, I could just say if John.age equal to Greg.age. So I wouldn't need equatable. Does that make sense? But you're trying to compare 2 custom types, like type to type, then you have to do equatable. And then for this one, hint. Do we want a hint? Yes? No? 10 minutes? Okay.
Because remember, there's objects you have to clean. Yeah, just the objects on the yeah. So not the
Again, we're not comparing the properties of the fellow, we're comparing fellow versus fellow, right? So I'm not saying fellow that cohort, I'm saying is fellow more than fellow two, right? Example here, right? Fellow one is more than, right? Not fellow one that cohort. It's being sneaky.
How would it, does it know to tell the difference?
Ah, that's the question. Does it know to tell the difference? That's the question of the day. That is the question of the day. Cannot compare to binary operators. Anybody has a hint? Actually, let me get to it. Okay, Tiffany's gonna do the first one, the movie.
Okay. So struct. And we're gonna call it movie. And inside the movie we have a name, which is a string, and we have.
Give me a space between your colon and the string.
Is that bothering you, Alex? And genre, we call it string again, and then I added a rating just so I could have a little bit of
Very nice.
variation.
Tiffany tomatoes.
I hope we don't get no tomatoes for my movies, but these are my movies. So I said bar fave movie is equal to movie. When we open the parentheses, it gives us what we need, and the name of it is Coming to America, because that is my movie. And the genre is that it is a comedy.
It's back.
And the rating, I give it a 9.9 because I wasn't in it. And then
Like a dog.
verbal sec fave movie is equal to movie. I couldn't think of a second favorite movie, so I just put anything, and I believe I put Diary of a Mad Black Woman. No pun intended. Well, man, the genre is also a comedy, and the rating, I gave it a
Drum roll.
8.2.
Eric is like 1.
Be nice. And then I put if fave movie. Oh wait, I have to put here for my struct. Sorry.
Before you do that, actually, just type it out and let's see what the error is.
Okay. If fave movie is equal to sec fave movie, then I want to print they are equal, or they are the same movie, same else print they are not the same.
And now, so now we see binary operator cannot be applied to the two movies, right? At that point, now we could go ahead and conform.
Let's see, our movie is equatable or equitable.
So now we conform to equatable. Compiler knows the properties to look for. It compares each property against the next. And great. Now we could run our program.
They are not
And they're not the same. Thank you so much.
Thank you.
Was anybody able to complete the second one? Not what? Say that again. Did you? Okay, so Brandon is going to come up and solve it. Thank you, sir. Sure. I'll hold it. Perfect there.
don't know what that means. Thank you. Oops. There we go.
Wait, before you do comparables, let's see what the error is.
Oh,
Because
okay.
we might not know what that means.
Okay.
Oh.
You see that?
So should I even include the static function?
Not yet.
Okay. Well,
Like,
I'll just
yeah.
I'll do everything else.
So yeah, exactly.
Okay. Oops. Oh. Oh no, did I tell everyone the answer?
Okay.
And then that is it.
So Brendan created a struct fellow. It has two properties, a name and a cohort. Cohort is a double. We have Mel from 5.0.
Even though you're not.
Even if you're not.
Yeah.
Which could be multiple places.
Two Mels.
Yeah. And we have Matt
Just do that for now. Yeah. I think it's
from
6.
6.0. And now we'll try to compare them using the comparison operator.
Oops. Oops. Cool. Okay.
Do you have it? Yes.
So yeah, cool.
Now at this point we have an error, right? The error says binary operator cannot be applied to the two fellow operands. Very similar to earlier, right? So go ahead, Mr. Brandon. How do you solve this?
So I put the comparable.
So he's going to conform to comparable. What does comparable do?
Compare the. Oh wait.
It gives, yeah.
Oh, okay. I was gonna say compares the.
It gives us access to the comparison operator, right? So now we could take two custom types and compare them to each other. We could say, does object one, is it greater or less than? We could do that using the comparable protocol, right? So now we could compare Matt and Mel. Go ahead. Static. What does that do?
Oops.
Modern. Less than operator. Ah, fixed, but what is that, right? He's gonna type it out.
Type it out because.
All right, if you're on the whiteboard, the whiteboard doesn't have fix it.
That's true. Chess.
Yeah, very good.
Chess.
So this is new, right? We see a less than sign here. That's the name of the function, by the way. It's an operator overload. What's that? It's L.
RHS.
It's LHS. LHS. L, not one.
Oh, oops. I'm sorry.
So LHS stands for left-hand side, right? Left-hand side, LHS. RHS, right-hand side of the operation. In that case, the operation here is the less than sign. Everybody with me? Yes, sir. Use that convention. LHS, yes. For left-hand side, yeah. Yeah, it's Swifty. Go ahead, you did it, right?
Yeah, I think it's all.
Okay,
good.
go down, run the code. So in that case, what do we get? Matt is still, right? Because obviously Mel is greater than, no, less than, sorry. Matt is less than, what do you have there? So
Did I just do my math wrong?
I think your print statements might have to be,
Oh,
I would probably do a different print statement here.
okay.
So Mel is, if Mel is less than,
If no, it's first side. Oh, okay.
Probably say Mel is in an older cohort, maybe.
Oh, okay.
Does that make sense?
Okay. So wait, should I just, switch it now?
For the print statement.
Okay. So
Like put like a, because the print statement might throw us off.
okay. Now.
So if Mel is greater, that means she's in a,
Is,
wait, no, the most recent. She's in the most recent cohort.
oh, okay. So just switch it.
So
okay.
yeah.
Switch. Most recent. And then for Matt, wait, something else. For Matt.
He's in a, he's an alumni or something.
Oops. Let me do that.
He's an alum. So that would be Mel here. And for that one, just say Matt is an alum.
Matt is an alum.
Okay. Let's go up to your static function and let's see what you're doing. Okay. So here you need to do more.
Here.
Right?
Okay.
Thank you, sir. So Brendan left us here with return false. That's not enough, right? What we need to do, thank you, sir, by the way, thank you, thank you, thank you. What we need to do here is define what we comparing. Everybody with me? In that override function or in that static function that comes with comparable, you need to say what you're doing. In that case, logically, we want to compare one cohort versus the next cohort. So here we'll say return left-hand side dot cohort, right-hand side dot cohort, right? So you want to define what you're actually doing as far as like logically in that comparison function. And again, we conform to comparable. Comparable says you need to implement one of those comparison functions. It's a static function. It works on that type, right? And here we're saying return if left-hand side dot cohort is less than right-hand side dot cohort, return true. Everybody with me? Right? So it returns a Boolean value. Takes in two types. The first type is the fellow. It takes two fellows. The left-hand side, again, it's an operation, two operands. Operand 1 is the left side. Operand 2 is the right side. Okay? So at the bottom, it looks like this. So example, we have Matt. Matt or Mel is on the left side. On the right side, meaning on the right side of this operation here, we have Matt. So Mel is a fellow. Mel is on the left side of the operation. Matt is a fellow. He's on the right side, right-hand side of the operation. Yes?
And it just goes by the order of where the instances are created. So whichever instance is first would be the left side, so the instance is second would be the right.
Based on how you pass it, like you see here, this would be the right side, the left side, sorry. Mel is on the left side.
Right, but that was the first instance. So I'm asking, is it off of the order of instance?
That you created? No.
Because when you pass it, you're not specifically telling it.
You are. When you call this function here, this is the left side. Everybody, this is the left side of the operation. This is the right side of the operation.
Now, the sign itself is backwards. So
The sign itself is backwards. Let's verify that it does do what it needs to do. So Mel here, Matt is an alum, right? Which makes sense. Matt is an alum. Where is Matt? Matt is, oh, so this is wrong, sorry. We need to do one more operation here. Let me run this again. So Mel is still in the recent cohort. This is false. What are we doing here? Left hand side is one second. Let me just verify my function here. I have a little error. Turn. Left hand side is greater than, return true. Let's see what happens here. And we'll go over this together again. So Mel is 5.0. Why is this? This is wrong here. Mel is less than. This is false. This is false. This is off, right? So if Mel is less than Matt, in that case, Mel is less than Matt, we're going to say Mel is an alum. Does that make sense here? And if it's not, then we have Mel is in the current cohort. Mel is in the current cohort. All right, that makes more sense. Let's run this. Okay, Mel is an alum. That makes sense, right? Because 5.0. If we say, change that to Matt, if Matt is greater than Mel, it's going to change it anyway. Sorry, let's just keep this one example. Don't want to confuse us more here. Keep that one example. This one works. We could have a next example at the bottom to test greater than, in that case, Matt. But let's go over the functions. That's more important. Here we have our comparable protocol. We have our static function, our greater than. This is an operator overload. You could have your own operators being overloaded in Swift to have a function name. So here we have comparable overloading the comparison operator. On the left-hand side, we have a fellow coming in. So here we're returning true if the left-hand side is greater than the right-hand side. And if we're doing the less than operator, we return true if the left-hand side is less than the right-hand side. Okay? Questions?
So we can choose any one that we want to do, but we just want to make sure that when we're doing our comparison, operators match.
Yes, we'll do an next example. Let's do an exact example with Matt, right? So Matt here, let's say if Matt is greater than Mel, here, we'll say print Matt is in the current cohort. Right, so those are two different examples. Else, print Matt is a graduate. Bless you. And run it again. So Matt is in the most recent cohort. That makes sense because Matt value is basically 6.0. We're comparing 6.0 versus 5.0 here. And here we're comparing 5.0. Is 5.0 less than 6.0? Right? So that's the comparisons we're doing here. Is 5.0 less than 6.0? Right? And here is 6.0 Matt's value, is it greater than 5.0? Everybody? Right? Those are the comparisons we're making here. We could go one step further. Yes?
Right. Let's say there's the static function we have something to return the code right there. But what if we had a company that was like either age, we wouldn't be able to do that we have to create another static function that
Yes. Yes. But it depends on, at the end of the day, what you want to compare. Like, how do you, as the developer, how do you want to compare your objects?
so ideally you only make one case static function.
Yes, in that case.
You're deciding what you're going to compare.
In that particular case, yes. Question?
How would this be for
That's a good question. As your, like you have is 5 less than 6 or whatever it is. So now I could have it on my custom type. I could compare my custom types to each other. It gives me that flexibility to do it. Yes, you could use the properties as well, but you might get into a use case where you want to compare one person or one fellow versus the next fellow based on some criteria that you have. With that fellow, it would make more sense to have like a cohort, for example, right? Is that fellow, if you want to do a sorting algorithm, for example. Yes, you could say sort by fellow.age, but we need to know how to use comparable there if we want to compare one object versus the next object. Yes, on the property, yes.
So it's possible to have both functions inside of the struct, but it will only look for the operand?
The one you're currently using, yes. So in that case, whichever one we call in, it will call. I was about to put a breakpoint, but I can't put a breakpoint here. Let's just put a print statement. So print got called, and then here just put a print statement. Print less than got called. So we can use a breakpoint in playgrounds, but let's just put a print statement and see what that looks like. So I'll stop it and I'll play it again. So here, both of them got called. The first one I got called, if we go down, did you guys print that out? The first one I got called was the less than, right? We were doing a less than operation, Tiffany. And the second one I got called was the more than operation.
Can you just scroll down to the two different
You mean down here?
Okay, yeah.
Right, so the first one is the less than, and the second one is the more than. Yes, sir.
So the reason it knows the comparison is greater than or less than.
Yes, because that's the same symbol that we use in the operation.
So we could change that to greater than or equal to.
It should work by the same, it works with greater than or equal to as well. Let's see, how can we make it? Let's create a third person. Let's create an X cohort and do greater than or equal to. All right, does that help you? Sorry, so let's create Eric. Eric is a third fellow and he's 6.0. So far so good? Okay, so we created a third fellow and let's go down to make a comparison with the third fellow. Everybody typed out everything? Is there any place I could go back for us to type? Are we all on board? Okay, so now let's go ahead and say if, what's Matt? Mel is 6.0, right? No. Matt and Eric. Let's compare Matt and Eric. So if Matt is greater than or equal to Eric, print they're in the same cohort. Else, print not in the same cohort. Right? So we got our print statement saying they're in the same cohort by using greater than or equal to. So it works as well because we still have the comparable protocol being used. So we don't have to explicitly write a function greater than or equal to. Cool? So we did those three scenarios there. We have greater than, we have less than, and we have greater than or equal to. You could do less than or equal to as well. Everybody sees that? Any questions? So we've seen three built-in protocols today. We've seen custom string convertible, we've seen equatable, and we've seen comparable. Let's actually go to the Swift documentation and see what those look like. So Swift custom string convertible here. Let me zoom in a little bit. There, so a type with customized textual representation, overview, types that conform to custom string convertible can provide their own representation to be used when converting an instance to a string. Right? So if you want to take your own notes, that's like what you want to take there. Their own representation. Remember when we said description, right? On custom string convertible here, that's what that means. Their own representation of what that instance looks like. Right? So that's custom string convertible. Might have an example here. And they have an example here. Custom string convertible, description. It started up, they have a point, a struct, it's a point. It has an X and Y. They try to print out, very similar to what we did, they printed out what the point is. And what the point was point parens X and Y. Everybody sees that? The next example was, hey, go ahead and we haven't seen extensions yet, but you could have an extension on your type. And now they have custom string convertible, description, and now instead of saying print point XY, whatever, it says print open parens 21, comma 30. That's easier to read than what this is. It depends on what context you're trying to go to. Everybody? Let me slide this out. Cool. And we were talking about properties. So somebody was asking earlier. So the only property we have is description. Who was asking that question earlier? Somebody was asking like how many, was that you? So you see the only one we have access to is properties. I mean description. There's no function, there's nothing. The only thing it gives us access to is description. So let's slide that over. Mel, you have a question? Fatal. Well, let me slide that out. So this is custom string convertible. Again, sometimes Apple does a great job with showing like an example code here, and this is an example of a great documentation. You talk about what the thing is, and then you show an example of it. Let's see a next. Let's do case iterable. Case iterable. Wouldn't that be nice if it just worked? Yeah, it did. Great. Consistency. So here, case iterable we saw from enums, a type that provides a collection of all its values. Again, which makes sense. On an enum, we conform to case iterable, we get all the cases in the enum. Let me slide that out. Case iterable is a protocol overview. Again, also gives us an example here. Great, great, great. Types that conform to case iterable are typically enums without associated values. It gets really messy if you try to do all that stuff there. So again, enums without associated values. You put case iterable on compass direction here, and now you get all the directions in a compass. Right? We've seen that example. Correct? Let's see equatable. Equatable, a type that conforms for value equality, right? Equality, equal, equal. Types that conform to the equatable protocol can be compared for equality using the equality operator, equal, equal, or inequality, not equal to, right? Again, very good documentation, got examples. We have an array of students, and we want to compare them. We go ahead and this, as I said earlier, as of 4.2, you do not need to explicitly have a static function for equal, equal, as we saw with our movie example, right? So before 4.2, you needed to explicitly say or write a function very similar to comparable. Everybody with me? But here, you do not need to do equal, equal with the static function. And lastly, we saw, did I start this out? No. Like that. And lastly, let's see comparable. Okay, comparable, a type that can be compared using the relational operators. So we have 4 relational operators. We saw 3 of them. We just didn't do the last example, but it's very easy to do the last example here. Less than or equal to. We did greater or equal to, I think. Comparable protocol is used for types that have an inherent order, such as numbers and strings. Many types in the standard library conform to comparable operator. Here we have a current temperature of 73. If current temperature is less than or equal to, so that works, obviously. It's an int, right? So int conforms to comparable. Let's see, they have a custom. So here they have date, which is a custom type that you create. Don't create date, by the way, because date is like its own type. I don't know why they use date here as an example. Do not do that. Because date is like a custom, date is a built-in type, right? So you don't want to name your own thing type here. And here they're conforming to comparable and they're passing in the less than operator and they say if. So you could have more instructions here. So if left hand side dot here is not equal to right hand side dot here, return this, else. So you could have more logic operations in your function based on what you want. So for people asking about multiple properties, you could have a mini, you could have multiple property operations based on what you want, your type to return. So this is the last one we'll talk about now. I will start that out. Great. Cool. Let me show you one more thing here. So people are asking about protocols. There's so many protocols, like there's an angle protocol here, character protocol, right? How does something become a character? It conforms to the character protocol. A single extended grapheme cluster, right? You have a date protocol. So if we go to, for example, let's go to integer or string. Let's go to string, Swift. And let's see what string conforms to. So if we go to the very bottom, if you want to see what a type conforms to, basically go to the documentation and go to the very bottom almost. String is very big. Why did I choose string? Okay, if you go to relationships, to the very bottom of any type in Swift that you're looking for, and you go down to relationships, there's a conforms to title, and this is what string conforms to. Those are all the protocols it conforms to. Protocols we'll see later in core, as we keep talking about iOS development. Decodable and encodable, we'll see those a lot. Today we saw equatable. Hashable, a set is hashable. We saw that earlier, I mentioned that, right? It needs to be hashable in order for it to be unique, right? So that's the hashable protocol here. A dictionary, the key is hashable. Remember from dictionaries, right? We saw custom string convertible today. So that's what all the protocols a string conforms to, right? It needs to be a string protocol. We've seen string protocols a lot here. All right, so we'll stop here to talk about protocols. We'll go into the last topic of the day, which happens to be a complicated topic, but it gets us ready for tomorrow. Yeah. We'll talk about what is that? This one? We'll talk about delegation. So let's talk about delegation. In our lesson, let's go to the lesson. I added delegation at the bottom. Let's go to the lesson of the day. If we all go down to number 9 in our lesson for today, delegation, right? Delegation is heavily used in iOS development. Heavy. The quicker you could get familiar with like delegation and how to use it, the better your experience as an iOS developer will be. So protocols enables us to use delegation. What is delegation? Delegation is a design pattern. We've spoken about design patterns loosely, but what delegation gives us is an ability to have a class work on our behalf, right? We'll make an example today, but tomorrow we'll get a better context of what delegation is in built-in UI text field, what that looks like and how it's used. But delegation basically, according to Apple documentation here, is a design pattern that enables a class or struct to hand off responsibilities to a different type. So you have Brendan, right? He has a protocol. He creates a delegation of it. Mel goes ahead, she conforms to Brendan's protocol, and she works on his behalf. So anything that he says, whatever function that she is conforming to, gets updates from what Brendan is doing. So if Brendan goes down to the market, he buys stuff, as he's paying for stuff, if she's listening to what he's paying for, she gets updates for what he's paying for, right? So that's what delegation is at a high level, but we'll see it in an example today. If you don't catch it right away, that's okay. We'll do it again tomorrow. We'll keep doing it. It's one of those patterns. It's hard to conceptualize or to grasp like on day one, right? On day one, it's hard to get everything together. Very similar to like closures we saw. Delegation is a bit heavy of a topic to grasp and understand its different parts, like how it's all working together. But at a high level, know that delegation is on behalf of something, I'm listening for changes, right? I'm listening for changes. Every time it's an hour, I want to get an update from a clock, like an alarm or whatever it is. Whatever I'm listening for, every hour, give me an update, right? You go ahead, do your work. Every hour, I want to hear an update. You update, I get a notification, right? That's like how delegation works, right? You delegate a piece of work to somebody else. Okay. So we'll make an example of it. Here at a high level, we have a protocol which we've seen today. We have a protocol called Game Delegate. Game Delegate has two methods. It has a start game and an end game. That's a protocol. Any object here is a class restriction. This protocol says only a class could use that protocol. Not a struct, not an enum, only a class could use that protocol. I go ahead and I create a class called Blackjack Game. We'll type that out and we'll talk about it. But we have a class here called Blackjack Game. It has a delegate. That delegate, you could call the variable whatever you want, but convention, you should call it a delegate. So we have a variable called delegate, which is of type game delegate, right? So it's of that type, game delegate. And anytime you want to listen to changes on any part of your code here, for example, the game status, for illustration purposes, our game status says the game ended. So when the game ended, on my delegate, if somebody is listening to my delegate or conforms to my delegate, they'll get updates when the game ended. So on that delegate, I said game ended. I could pass in a score here. We'll first type that out and then we'll add a score. I think we have time for that. I could pass a score to whoever is listening to changes, right? So whoever is listening to changes on my game gets notifications like, hey, the game ended. Go ahead and change the view or show confetti, whatever you want to do, because now the game has ended. Going to the person listening to the changes. The person listening to the changes is the class that's conforming to the game delegate. Blackjack view controller, Blackjack view controller here conforms to the game delegate. If it conforms to the game delegate, it needs to, look at that, it needs to now implement a start and an end game function. Do we agree? Right? Because this morning we saw, if you conform to some protocol, you need to implement the methods and variables of that protocol. Right? So here, I'm conforming to this protocol, game delegate. I need to implement end game and start game. So far, so good. So I implemented those two methods. I created an instance of the blackjack game. So now the blackjack game is in memory, it's playing, whatever, it's happening. I created an instance of the view controller. It's called blackjack view controller. Again, we'll come through that, we'll talk more about it. I'm just showing us initially what the thing looks like. Blackjack game, I set my delegate. So now I'm saying the view controller is the one listening for changes. Everybody. The view controller, that view controller here, that view controller is an instance of the blackjack view controller, right? We know instances, right? So blackjack.delegate is an optional. Let's look up here. It's an optional. It's an optional for a reason. It might not get set at any time. So it's optional, right? Here I'm setting that value right now. I'm setting the value here. I'm saying the view controller is the one listening for changes, okay? It's listening for changes. What changes is it listening for? When game status updates, I'll get a print statement. So when blackjack.gameStatus gets called, right? Blackjack game status gets called, right? When that gets called, that function gets called, the delegate gets updated. The delegate gets updated And that function gets called. The endgame function gets called, and it prints, look, looks like we have a winner. There's a lot of moving parts there. This is a big topic. We'll come to it a lot. Some of that, we don't need to use it right away because we're using built-in delegate methods, right? Like tomorrow when we start talking about UI text field delegate, we're not creating that from scratch. We'll be saying UI text field delegate dot whatever, view controller dot delegate is self, whatever. Tomorrow we'll be using that abstractly. We won't be seeing the inner workings of it. But at a high level, this is what happens in iOS. And iOS has a lot of delegation patterns throughout the operating system. But for now, my conforming class is the view controller. The view controller says, I am now listening for changes on that delegate. It does it by registering itself on the delegate object. So blackjack.delegate is view controller. So the view controller, if we look at the view controller definition here, this is the view controller. The view controller says, if endgame gets called, go ahead and print out, looks like we have a winner. And that's what gets printed, right? So let's do it as an example. And if we have time, which I think we do, we'll pass data. Because you could pass data here. When I say pass data, game status could pass data. It could pass the score of the game, right? Because the view controller might want to have the score to update its UI. So the game status could pass a score. So let's go ahead and implement that, and we'll have time, I think. I think we have time. But again, this is one of the things you'll see it for the first time. You'll be like, wow, I just don't get this. But keep doing it, and we'll keep using it throughout. Table views. Everything we're doing has like a delegate that you want to listen to. You want to listen to it? Hey, there's more data. Update my table view. Somebody entered some input into a text field. I want to find out information about it. Maybe I want to dismiss the keyboard. So all that has like a delegate. Listening for changes on an object. Basically, at a high level, that's what it is. It's listening for changes on an object. Somebody closed the door. I want to get updated. Somebody entered my house. I want to get updated, right? A new child was born. I want to get updated, right? That kind of thing there. Like somebody is listening for changes on some action. It's very similar to the target action with a button. I press a button, somebody gets updated. In that case, it's my method, my action method gets updated. Then I could change something. All right, let us go back to our playgrounds and let's have a header here. What's that, Eric?
It's cold.
It's cold. It's at 80.
It's at 60.
Next time, do a marathon with me, man. You'll still be hot today. Okay, so delegation. This is delegation, right? Let's review what we did when we come back. All right, so delegation here. I start out with a protocol here. My protocol is called game delegate. We're restricting it to classes, so we're saying any object here. We'll put some notes and say what that means. Function, we have a start game. And we have an end game. So any object, where should I put this? Any object restricts the game delegate protocol to only classes. Right. There's reasons for that, and those reasons will become more paramount as you get more into memory management, right? Because we'll see weak var. We'll wonder what that weak means. We'll explain what that weak means as we get more into memory management. But for now, we have any object here, and any object restricts our game delegate to work only on classes. So I have a blackjack game here. It has a function called game status. Blackjack game conforms to game delegate. Actually, it doesn't conform to game delegate, sorry. It has one variable, weak bar delegate, which is of type game delegate, which is optional. What does that all mean? Weak here, weak breaks strong reference retain cycles. Basically, I'll explain what it is. Like, basically when two objects has a strong reference to each other, that creates a memory leak. More on that later. Right? The more memory leaks you have, the slower your app will run. Eventually it will crash because it's just grabbing a lot of resources from the phone. So we want to avoid strong references. So to avoid a strong reference to that delegate object, we set it to weak. Okay? If you do not say weak here, this is strong by default. We saw strong and weak in IB outlets, right? So here I need to explicitly say weak in order to break that retain cycle. More on memory management later. Okay? For now, never submit code like this. Right? You might not get any feedback from the person, but basically what that's saying is you're creating a retain cycle, right? You're creating a retain cycle, you're causing memory leaks, your app is taking a lot of resources, eventually it will crash. As a developer, you don't know what you're doing, so that feedback is not gonna, you might not get feedback there. So make sure that you're breaking the retain cycle by explicitly saying it's a weak reference to the delegate, which makes sense too, because here our game delegate is an optional. Why it's an optional? It might not get set. When this object comes alive, that object could be nil, which is fine, right? Great, so here we have our delegate object, we have our game status function. All what game status does for now, it sets the delegate, it takes the delegate object. Whoever is listening to game status changes, for example, will get a notification here on our game status, on our end game, sorry. Look at that. So when the game ends, whoever is listening or whoever registers themselves for the delegate, whoever conforms to the delegate, in our case, the view controller that we saw earlier conforms to the delegate, it will get changes when game status gets called. And those changes, it only gets updates because explicitly we said, hey, if you're listening, Mr. Delegate, the game has ended. That's it. Cool. So let's go ahead and define our blackjack view controller. What do we have here? We have a class, it's called blackjack view controller. Conforms to UI view controller, sorry, inherits UI view controller, and conforms to our game delegate. That. Okay. For now, let's just do the fix it because we've seen how to explicitly write the requirements of a function. So if you press the fix it button, you'll get the two stubs. Those are the two functions required. Those are the two functions required by the game delegate. If we look at the game delegate again, the game delegate explicitly says, I'm requiring whoever is conforming to implement a start game function and an end game function. right? If I'm saying I'm conforming to game delegate, I need to provide the implementations of start game and end game. As far as like what is inside the body, it's up to you. It's up to you what you put inside those two functions here. Okay? For start game, we'll simply say print blackjack started. And end game here, we'll say print looks like we have a winner. Great. So this is our blackjack view controller. Nothing much happening here apart from implementing the two required methods. And we'll go on, we'll create an instance of our blackjack game. So blackjack game, we'll create an instance of it called blackjack game. And we'll create an instance of our view controller. Of our blackjack view controller. Awesome. So here we'll say this needs to be, this is required. So required to, no, in order to get, I'll say notifications here from the game, from the blackjack game, we need to set the delegate and assign the conforming class. What does all that mean? That means basically we have our blackjack, right? We have our blackjack instance. Our blackjack game instance has a delegate, right? That delegate, we're saying the view controller is the one listening for changes, right? So that view controller here, view controller instance is registering as a delegate of blackjack game to listen for changes on the game. Okay? So here, if you do not put that step in, which we'll see, we'll miss a lot, and we'll be like, hey, why are we not getting notifications? Or why isn't our table view loading? Or why aren't we getting notifications from the keyboard? Whatever it is. This is the step, like if you do not register like who is listening for that delegate changes, you're not gonna get changes, right? Basically here. It's like you have your TV on, you put a station on. If you don't put it on a particular station, you're not gonna get that news coming in. So here you need to say my delegate is listening. Who is listening? The view controller is listening. And our last step, we'll just go ahead and say blackjack, call game status. Again, blackjack game status, in game status function, in the method, it has the delegate dot endgame, right? That's how we get notifications there. A lot of steps, we'll go over it again, but don't be too overwhelmed because that design pattern, it takes a while to get used to. So I'll go ahead and test my application out. If it does work, I should get a print statement from my game status delegate, which I do. It says, looks like we have a winner. Okay, that's, let's step back a little bit. Let's step back. Let's make sure everybody typed out, then I want to explain again. Did we get the protocol typed out? Yes, good. Did we get the blackjack game typed out? Do we have the blackjack game typed out? Okay. Do we have the blackjack view controller? do we have the two instances? An instance of the blackjack game and an instance of the view controller. Yes? Okay. Did we set our delegate? Did we set the delegate? Did we set it? Okay. Did we call game status? Did we call game status? Okay, good. So let's go tap down again. Again, in iOS, protocols, delegates are heavily used, right? There's a lot of classes that have UI where if somebody changes a UI, you want to get some notification about that particular UI. How you get those changes? iOS uses delegation pattern. Delegation pattern, your view controller registers as a delegate on some UI element. Example, UI text field has a delegate. UI table view has a delegate, right? It listens for changes there. And your view controller in our case here, our view controller, implements or conforms to that delegate. Example, we could have, instead of like game delegate here, tomorrow we'll see UI text field delegate, right? Also, there's UI table view delegate, right? UI collection view delegate. At some point, you'll be like, why isn't there a delegate for this thing? I want to get notifications. I want to know when there's more data, right? So here we have a game delegate. Tomorrow we'll see UI text field delegate. There's a bunch of methods there. On our own custom delegate, which we created today, it's called game delegate. Game delegate has two methods. One is called start game. Let me know when the game started. And one is called end game, right? On our blackjack game, that's the game that's being played, blackjack game has a property. That one property it has is called delegate. It's of type game delegate. Why do we have this game delegate here? We want to know, or we want to let the view controller know, or whoever is listening for changes, when the game status function gets called, go ahead and pass endgame. Endgame right now doesn't have any arguments, but you could pass data. You could pass data to the view controller. What's a good piece of data to pass to the view controller? A score would probably be a good piece of data, right? The view controller probably wants to know what the score is. What's the score of that game, right? Your view controller might want to know that because your class itself lives somewhere. When the game is being played, you want to update the view controller. You update the view controller. Now the view controller knows that the game ended. For now, we're not passing in any score, but we'll pass a score. We'll update that. My view controller runs. It's listening for changes, especially on endgame. It knows when the game ended. So here we run our application. Blackjack game status got called, and we got a print statement saying, looks like we have a winner. Where is that coming from? It's coming from the endgame function. Again, a lot of moving parts, but let's update the data part of it, and we'll open the floor for questions. So let's update our function. Let's update our game delegate function to take a score. So here we're passing score of type int. Keep in mind, your functions could also return. It could also return a type. I could return something here. I could return an int. I could say return int. This is valid. Everybody, right? We only saw delegation today for the first time, so know that your protocols could also, the functions could also return, could take multiple arguments, could return multiple parameters here, right? For now, our endgame has a score. That's what it has, a score. So let's update our endgame here with a score. So make sure that you updated your protocol. Endgame score, right, is an int. Everybody? And let's go and update our endgame here. So here we're just passing score. For now, we're just passing 21. We're passing 21. We'll go down here because this also expects some sort of argument here. For endgame, we'll say score is an int. Right? So we updated 3 places. In the protocol, in the game, in the blackjack game, and in our end game. So here it looks like we have a winner, and we could just pass in score here, like that. So score is score. So assuming you have a game being played, the game ended, and your view controller, that view that you're seeing on your device, it will update with whatever the score is. So we run our playgrounds again. We'll see, where is it? Sorry. I need to run the playground. Sorry. So here we have, looks like we have a new winner, and it's 21, right? I just hard coded 21 in there, but let's go ahead and not hard code 21. So let's get a random number for 21. So let's start out with saying score. I'm in the endgame function, in the blackjack view controller. So here I'll create a score, and I will use int.random to get like a random score being generated from whatever, say 18 to 25. That's valid. Cool. We'll use a switch statement here to say switch on score. Switch on score, and case 21, for example, print blackjack case case 20. We'll tell them still keep playing, right? Because you're less than 21 here, or less than 20, 20 plus. This means 20 and below. Everybody, the 3 ellipses there, if you haven't seen it, just a review here. 3 ellipses, 20 means 20 and below. Everybody? Okay. So keep playing here, and case 22. Print, let's say, score not available. All right, so we have a score. We picked a random score, and here we switch on score. Case 21. What am I missing here? I'm missing a parents. Case 21 is blackjack. You less than 20, keep playing. You over 22 or over 21, you busted. Great. So now I will remove that print statement here. Keep playing, show the user the score. Busted, show the user the score with a score of score. All right, blackjack is doing the score, blackjack is 21. All right, let's run that again and see what happens. Okay, so I busted with a 25. Anybody got blackjack? No? No lucky person here. Busted again, 24. Nobody blackjack? You blackjack? Nice, very good. Yulia is the winner of the day. Okay, cool. So here we have our end game, our view controller. Everybody got the switch statement typed out? Can I go down? Okay, so let me clean that function up a little bit, make it tighter. Okay, so here we have our view controller listening for updates. Again, this is all in one file. It's going to be hard to get context for what's happening. But what I want us to leave with today is delegation is a pattern in iOS where has other classes listening for changes on an object. It's listening for changes, whether it be, most changes we're listening to is on a UI element. Somebody clicked in a text field, it wants to listen to changes. The user did begin typing. That's actually a method. User did begin typing, I probably want to do something with my view or my screen. I want to show something. The user did end typing. I probably want to get rid of my keyboard. Right? There's a lot of moving parts there that you want to listen to explicit changes. So we have delegation as part of that pattern we could use in iOS. Everybody with me? Here I just showed us for illustration purposes how delegation pattern became a thing. How is it possible? It's possible because we have a protocol. We have a protocol here, right? On that protocol, we could have a set of methods or properties that whoever is listening to needs to implement them. As we talk more about UI elements like UI table view controller, when I talk about a table view controller, imagine you have a grocery list. We all have apps here, maybe like we have a grocery list or we have the Notes app, right? We scroll through, the thing you're scrolling through is like a table view, right? You have different lists, different grocery items. That's what I'm talking about when I say a table view. So it's very similar to like we have a UI label, we have a UI table view, we could drag into our scene. Everybody with me? So that's what I'm talking about when I say UI table view. So imagine you have a UI table view. The two things we need to know on a table view, the items for that table view. How do I populate that table view? How do I know how many groceries I have? Or how my shopping list, how many items do I have in my shopping list? All that stuff there is made useful, or we know that information through delegates. The delegates needs to know how many items in the table view. When I swipe and I delete, the delegate gets updated, right? So all that there is using the delegation pattern. Let's see, for tomorrow, if we could start looking at the lesson offline, not now, but for UI text field, it would be nice if there was like a view of a text field there. You need to start putting like UI stuff. Okay, there we go. Perfect. Perfect. Let me zoom in. Thank you, Apple. So here, do we see where it says URL here? So the user selected on the left side, user taps a field. Do we see that? On the right side, they're about to enter a URL. Right? So that URL here, that's a text field. A text field is where the user could put in input. So tomorrow we'll start seeing how to implement that. On a UI text field is very similar to our game delegate. Everybody with me? Actually, no, not our game delegate, but just our game. Right? Just our game, if we go back to our... So the UI text field is very similar to our blackjack game. Everybody? On our UI text field, we have a delegate. It's called UI text field delegate. So it's very similar to our game delegate here. We've seen a protocol. That protocol in our text field is called UI text field delegate. Everybody with me? So I'm trying to make comparisons between what we'll see tomorrow and what we did today. The comparisons are the blackjack game is very similar to the UI text field. What the user enters. Our blackjack game is a game being played. The changes that's being updated, those methods that you have to implement, in our example here, UI text field, if we go to our UI text field delegate, UI text field delegate here, let's take a look at some of the methods that we have. Right? Here, managing editing. Text field did begin editing. When the user starts to type in information in the text field, we have a delegate. We have a delegate that we could implement on our view controller. In that delegate, we could do any logic we want. If the user started typing, maybe we want to change the UI or do something with the UI. So here, again, very similar to our game delegate, we have methods. Those are methods on the delegate. That method here is optional. I spoke about optionals earlier a little bit, but that particular method is optional. I do not have to implement it. Everybody with me? On our game delegate, all those methods are required. All methods here are required. All those methods here are required. But on a UI text field delegate, all the methods are optional. Again, all the methods on a UI text field delegate are optional. It's up to you if you want to implement them. Right? Everybody with me? A table view delegate, there's 2 required methods. We'll talk about it next week. We'll start talking about UI table view. But on a UI text field, the delegate methods are optional. Some of them actually do list it for you. Yeah, there we go. So I clicked on text field should begin editing. Look, do you see the optional keyword? It's optional. It's up to you if you want to implement it or not. Okay? Again, we'll see more use cases tomorrow of this. But for now, know that your delegate methods could be required or optional. Okay? I'm not going to show us the syntax for optional right now. Just know that it could be optional or required. If it doesn't explicitly show optional, it's required. In our example here, start game and end game are required. Why? We have to implement both here in our view controller. In our view controller, we have to implement start game, we have to implement end game. If we do not implement one or the other, we'll get a compiler error. So far, so good. Okay, so here, they're marked optional. If you want to see what that looks like, it's at the very end of the lesson. But again, the syntax becomes really, really quickly. But as we get more into creating our own custom delegates, we'll see how to make the methods optional. Just for introduction purposes, we showed you guys what delegation is, because we'll start using it tomorrow and throughout a lot. So to know how it works, then how it works is today. How it works again, we'll introduce it again next time, where you create your own custom delegation. Okay? But for the purposes of tomorrow and throughout Unit 2, where we'll be using a lot of delegates, knowing how it works, like the underneath lines of it, is what we did today. Okay? We might have one of the lab questions asking you to solve one of those problems here, so you have the context of it. Great. Any other questions? Okay, so we'll stop here if there's no more questions. But let's see what we did today. We did a lot-ish today. We spoke about protocols today. We said a protocol is a blueprint that lists properties, methods, or initializers. We could also have initializer here. I could have like some initializer here. I'm not gonna do a case for now, but I could have an initializer here with age like this, right? And the conforming type needs to implement the initializer, right? So we have properties on a protocol. A protocol is a template. It doesn't define, or it doesn't implement, rather. It doesn't implement what this variable is. It doesn't implement what that some int is. It doesn't implement the method. It just lists what the thing should be. We went on, we said some struct conforms to some protocol, and now that some struct needs to implement some string. It needs to implement some method with its own body here, okay? We went on, we spoke about, we did some more examples. We had a protocol called race. Race had type, distance, and name. We had a marathon, which conformed to race. We spoke about the get and the set here. Get is read-only, or a computer property where it's read-only. If you have a set and get, marathon here needs to implement a way to set the marathon name, right? When I say it needs to implement a setter, this here is implementing a setter. Now my variable is able to change because it's no longer just a computed property. This is a computed property. This is a computed property. It's a get only. It's a get only property, right? We said our struct could have its own properties here. We have our own property called location. Mr. Kelby came up and he created a protocol called human. Human has 3 properties and a method called drink. Mr. Kelby created a struct called Kelby and an instance called Kelby, right? Kelby returns a computed property 7 hours of sleep, right? He created an instance of Kelby and he said Kelby drinks. And Kelby drinks returns, my name is Kelby, I eat food, I sleep 7 hours a night. We created an next protocol called fully named, right? Fully named had one property called full name. It's a getter. We implemented person, right? Conforms to fully named. And our object could have multiple conformants to protocols, as opposed to a class where it has single inheritance, right? An object could have multiple conformants to multiple protocols. Here we're conforming to protocol 1, protocol 2, protocol 3, right? Description, where does description come from? Description comes from custom string convertible. When we conform to custom string convertible, we're able to override description with our own string. So now when we say person instance when we say print person instance, we get the person's full name, the age, and the occupation. We did that example here with print John. When we printed John, we got John Appleseed is 56 years old and is a web developer. So that's great. We saw our first built-in or our second built-in protocol, the first one being case iterable on enums. We went on, we created our own exercises of our movie struct, which conform to equatable. Equatable give us equal, equal, right? Or not equal. Or you could also say movie not equal to movie 2. You could also say movie 1 is not equal to movie 2 when you conform to equatable. We tested it here. We said, well, not me. Tiffany tested it here. She said, if favorite movie equal to second movie, then they are equal. If not, they are not the same. Great. And our last exercise was to create a fellow, 2 instances that conforms to comparable. Why comparable? Because we needed to compare, is one greater than the other? Is fellow 1 greater than fellow 2? Or is fellow 1 less than fellow 2? And for that, we returned left-hand side dot cohort is greater than right-hand side dot cohort. We tested it here. We had 3 tests, less than, greater than, and greater than or equal to Eric. And we came into our last topic of the day, which is delegation. And we said delegation is a design pattern in iOS that enables one object to listen to another object. Delegation is a design pattern in iOS, or in Swift, not just iOS, in Swift that enables object A verifications on object B. We created our own custom delegate here. It was called game delegate. We use any object to restrict our object to only classes. We have 2 required methods. We had our start game and we had our end game. End game has a score of type int. Our class blackjack game has a delegate variable that's type game delegate. It's optional. Maybe it's set, maybe it's not, so it's optional here. Game status simply says, hey, when the game status gets called, go ahead and notify any delegate that's listening to the end game here. And end game passes the score. If the score is 21, which we hard-coded here. 1 second. Let's update this, actually. No, this is good. What's it? End game. Oh, okay. 1 second. This score should have been up there. This is This should be not here. This should have been in here. Sorry. And pass score here. So update your game status function. That's where we capture our score, make it random. Pass the score here. One second. So make the score random here. Okay, I know what I'm gonna do, sorry. One more thing, take the score here. Only make the score random in the game status, and then in the end game, check the score. Okay, that's better. So in game status, we have our score, which is a random number from 18 to 25. On the delegate, we pass the score, right? On the delegate, we pass the score. On the delegate, we pass the score. We go down to the end game. End game gets a score, right? In the view controller, remember, it's listening for changes. And those changes, the only change we're getting right now is on the end game method, right? So on the end game method, we get the score. And in the score, we use a switch statement to say what the score was. So small update. Yeah. Where we change it, right? In the game status, yeah. Again, that makes more sense, right? Because the delegate doesn't care about the UI. It shouldn't care about the UI. The UI is up to us what we want to do with that score, right? It's up to us what we want to do with the score. Or what we get back is a score. We get back a score, and that's it. And then in the view controller, that's where we use the score and the switch statement to update the UI. In our case, we just updated the console with the print statement, right? For the view controller? Let's go down. Let Eric finish first. You done? All right. So a little refactoring to make more sense here. So in the end game, that's where we have the switch. Cool? That score is coming from the delegate. It should work still the same as before. So if you press, yeah. Question? Hey, I got blackjack finally, by the way. After 20 tries. Yes. When you put score inside of game status. Are you not using it? Yeah, but are you passing it here? Make sure you're passing it. Make sure you're using it. If you're not using it, make sure you're using it in the score, colon, score. Cool? All right. Okay, so again, a bit heavy of a topic, but it's going to be easier and easier as we go more into use examples of it. So far, so good? All right, thank you for that.